All right, Algebra 2, we're going to move into section 8.4 here. And what we're doing is we're talking about rational expressions here. And then we're going to do three types of problems with those. We're going to simplify some rational expressions, and then we're going to multiply, and then we're going to divide. But before we get into that, let's just take a quick second here and talk about what it is that we're doing here within Chapter 8. We're talking about a new kind of function here in Chapter 8, and that is a rational function. And what I want to make sure everybody understands before they get out of Algebra 2 here is that when we talk about a rational number or a rational expression, this is basically a fancy mathematician's word that basically just means that we are talking about fractions. A rational number is anything that can be expressed as the quotient of two integers. Well, rational expressions are expressed as fractions as well, and I just need to remind everybody that fractions, like the kind that you see in this box right over here, fractions are division problems. So when I ask you, hey, what does A over A equal? Another way to look at that is, what is A divided by A? So, as we get into simplifying, the first key concept that we're going to talk about right here, I've kind of got it written in two different ways within this box. The first one right here, A over A, or if you wanted to look at it, A divided by A. What I'm hoping everybody can tell me here is that A, which represents any number out there in the world, divided by itself is always going to equal 1. Any number divided by itself will equal 1, like 5 divided by 5, 11 divided by 11, negative 13 over negative 13. There's only one little warning though here, guys. That is only true if A is not equal to, the one number where this wouldn't work is 0. 0 divided by 0 is undefined. It doesn't equal 1. So that's the main big concept right here. Anything divided by itself is 1. And then kind of an extension of that concept right over here, if we had a factored expression. Factored means two numbers that are being multiplied. So A times B, that's a factored expression, and A times C, that's a factored expression as well. If you've got a problem like this, those identical factors of A on the top and the bottom are just going to cancel each other out, kind of the same way that they did over here on the left, and we're going to end up then just with the answer of B over C. Those A's will cancel each other out because, and let's get the wording right, guys, because they are identical factors on both the top and the bottom. But, and I don't always do this with you guys, but I do want to put something in your notes right here that's just a common mistake because I want you guys to write it down and see it. What a lot of people do wrong is they take what we just demonstrated right up here on the top right and they misapply it to this situation right here. A plus B divided by A plus C. And what they want to do, everybody, is to cancel out those A's right there, just like I canceled out the A's up here, and tell me that this is equal to B over C as well, but that is not the case. And that's why I have a big fat not equals to sign in the middle there. Now, what I'd like to do real quick, and you guys are welcome to skip this part if you want, I'd like you to demonstrate here that both of these concepts here are right. So if I were just going to pick some numbers, like if I was going to let A equal 2 and B equal 3 and C equal 4, let's take a look at what it is we're trying to illustrate right here. A times B, which would be 2 times 3, all over A times C, which would be 2 times 4. Well, let's see what happens there, guys. The 2 times 3 on top is 6. On bottom, the 2 times 4 is 8. And hopefully everybody can tell me 6 divided by 8 is equal to 3/4, which, if I had just noticed that the 2's were identical factors right at the beginning, identical factors cancel each other out and just leave you with this B over C right here, which is the answer of 3/4 that we were looking for. So that kind of seems to illustrate that what we wrote here is correct. You can cancel out the 2's, top and bottom, because they're being multiplied. But if I tried the same thing right down here with addition, let's see if that works. A plus B, all right, so that would be 2 plus 3 all over A plus C. That would be 2 plus 4. Well, if I do the addition on the top first, 2 plus 3 is 5. 2 plus 4 on the bottom is 6. And there's nothing we can do to simplify that. The answer is 5 over 6. But if I tried to cancel out the A's here, this is not going to work. If this 2 cancels with this 2, we just end up with an answer of 3/4. And 3/4 is not the same thing as 5/6. As a decimal, that's 0.75, and 5/6 is 0.83 repeating. There's other ways of checking that too, but that's just going to give you one quick counterexample to show you the danger of this idea right over here. So the difference right here, guys, you can cancel out identical factors on the top and the bottom. Factors because they're being multiplied. But here, the A's are being added. Those are terms, and you cannot ever cancel out terms, things that are being added. Okay, so with that in mind, let's knock out two examples right here and see what we got. This first example here is really kind of a fifth grade math problem right here, guys. That's a little weird. All right. Anyway, let's see what's going on right here. 168 over 192. Now, it's possible I could have given you a problem like this where the answer, the fraction can't be simplified. What I would want to do is play around with some numbers here that look like they might go into both 168 and 192, and then I want to kind of prove my point. Now, if I was with you guys live in class right now, I'd give you a couple minutes and say, grab your calculator and find me some numbers that you think divide into both 168 and 192. And invariably, people go the wrong way about this. They try to start giving me small numbers. They would say, well, Mr. Fontana, they're both divisible by 2. Well, that's correct. But we could be here for a long time if you're going to keep looking for small numbers. What we should do instead is start to look for some big numbers. So what I'm going to do here, guys, I'm going to open up this other calculator here. Let's do this guy right here. All right. And what I want to show you is a little trick right here that is pretty helpful for finding your greatest common factor. Now, the two numbers I gave you there were 168 over 192. I'm going to subtract those two numbers, 192 minus 168, and I get a difference here of 24. That number, whatever that difference is the biggest possible number that might be the GCF of those two numbers. So now I'm going to check it. Does 168 divide evenly by 24? I have no idea. So I hit enter. Oh, and it worked out nicely. The answer is 7. And since I now know from the first line here that 192 is 24 more than 168, I think this is going to work out as well. 192 should also divide evenly by 24. It goes in there 8 times. Now that trick I just showed you won't always work, but 24 is the largest possible number that could work out. So then if that didn't work, you might want to try something like half of that number, which in this case would have been 12, or some other factor of it. So as it is right now, it looks like 24 goes into both of those. So I'm going to factor this now into 24 times 7 in the numerator, and then that 192 was 24 times 8. And I wanted to do this problem with you guys to remind you this concept that I just introduced to you on the previous slide right here is a concept you've been using ever since you learned how to simplify fractions back in 4th or 5th grade. Those 24s are identical factors. Factors because they are being multiplied on both the top and the bottom, so they just cancel each other out completely, and we end up with an answer of 7/8. And obviously, I hope, there's no common factor that divides into both 7 and 8 other than 1, so that's how we know that we're finished with that problem. Now in example B, this one looks significantly harder than what we just did. It's actually not a whole lot different here, guys. This is really like 4 different problems all thrown into one. Now, what do I mean by 4? There's 4 things you have to consider in both the numerator and denominator. The numerical coefficient, the x factor, the y factor, and the z factor. And I got to look at those on both the top and the bottom. So let's start with the numerical coefficients. 9 on top, 45 on bottom. What is the greatest common factor that can be divided out from both 9 and 45? Well, hopefully that one's not too hard to see. That one's going to be a 9. The 9 on top gets divided by 9 and leaves us a 1. And in the denominator, the 45 divided by 9 is a 5. So everything you've learned about simplifying fractions in the past is still at play right here. Now, Let's talk about what's going on right here in the numerator and the denominator. We have got 5x's in the numerator and 2x's in the denominator. Now, what x to the fifth really means, let me write this down on the bottom, guys, is x times x times x times x times x. And in the denominator, we've got x times x, two of them. And what happens now? The x's get into a war. There's 5 x's on top, there's 2 x's on bottom, and what often happens in war, some of the armies kind of cancel each other out. This x wipes out this x, or better yet, they wipe each other out. And the same thing happens with this second x on top and this second x on bottom. And now the war is over because the bottom has nothing left to give. So we're left with how many x's? 3. And where do they belong? Up on top. So in my answer, I'm going to put an x cubed up there in the numerator. Okay, now we do the same trick with the y's. There are 7 y's in the numerator, 3 y's in the denominator. So they get into a battle now, and who wins? Well, there's more y's on top, and there's 7 right there. Minus 3 is going to leave us 4 y's in the numerator there. So we end up with a y to the fourth in the numerator here. Last thing I've got for you, z to the 10th on top is getting divided by z to the 10th on bottom. Uh-oh. And what happens here? 2 equally sized armies are going into war. This isn't going to end well for either one of them. Z to the 10th on top and z to the 10th on bottom are identical factors. They cancel each other out completely. Or another way to look at it is nobody survives that war because all 10, battalions or platoons or whatever they have wipe each other out. The Z's are completely gone. This is your final answer here, guys. And the one thing I'll tell you, you do not need to have the 1 in front of that x cubed y to the fourth. And oh, that's not what I wanted right there. Sorry. So that 5 would look a little better if it was centered, but there you go. X cubed y to the fourth all over 5. Okay, and just for the sake of argument, let's just say, don't change this in your notes, that I made this y to the 13th. Now, there's 7 y's on top, 13 y's on bottom. There would have been 6 y's left over. They would have ended up in the denominator. Why? Because now the denominator has more y's than the numerator. So you certainly can end up with some of those variables down in the bottom. But as the problem was written, there we go. This would be our answer to example B. And on to example C, this is probably the most important one. Basically, guys, this section can seem a little bit complicated, but there's really just 2 things you have to do to simplify these expressions. Number 1, we have to factor. And then number 2, we cancel out any identical factors that we have. But it's really important that you guys understand that we have to do these things in that order. Factoring first, and then you come back and cancel. So let's see what we can do in the numerator here, everybody. In the numerator, the first step to any factoring is to pull out a GCF, and I think we can see we have a GCF of 3. So in parentheses, that's going to leave us with an x squared minus x and a minus 20. Down in the denominator, 5x cubed minus 80x, we can pull out a 5, and it looks like we can bring out an x as well. And then in parentheses, what's left over? That'll be an x squared and a minus, if I'm not mistaken here, guys, 80 divided by 5 is 16. There was one x there, but we pulled it out in front, so that's it. X squared minus 16. Now, we've done some GCF factoring. That's usually not all we can do. Usually we can go a little bit further, and I think we can here as well. Now, the 3 doesn't go away. But what we have here, everybody, is a quadratic trinomial, which usually factors into the product of 2 binomials using reverse FOIL. So looking at it here, we've got an x squared, and that will get split up as x times x. Then I look at this minus sign right here. That tells me that these 2 signs on the right are opposites. One of them is a plus, one of them is a minus. And I need 2 numbers now that multiply to negative 20 and add up to negative 1. So those 2 numbers are going to be 5 and 4, better yet, negative 5 and positive 4. And you could check this using FOIL, guys. Your outer product would be negative 5x, your inner product would be positive 4x, and that adds up to the negative x that we needed right there. So, okay, I'm pretty confident there that we have done the factoring correctly up in the numerator. Now down in the denominator, again, the 5x doesn't go away, but what we have right here, I'm hoping you recognize, is a difference of squares binomial, and that factors into the product of two conjugate binomials. We take the square root of x squared, which is x, that goes here and here. Every time you factor a difference of squares, your signs are opposite, 1 plus and 1 minus, and then we take the square root of 16, which is 4, and that goes here and here. So, okay, guys, we have finished step 1 now. We've completely factored everything that we can. And now we move on to step 2, cancel out any identical factors that you have on the top and the bottom. So what do we see? The entire factor of x plus 4 cancels with this x plus 4. And unfortunately, you guys, that's it. You cannot cancel, for example, this x and this x. Why? Because those x's are being subtracted right here or added. You can't cancel terms. You can only cancel factors. You can't cancel out this 5 and this 5. Okay, because this 5 again is a term being added or subtracted. So can't do any of that. Everything we have here is going to be left over in our answer then. So our numerator is going to be 3 times the quantity x minus 5 all over. We've got a 5x in the denominator times an x minus 4. There are no other identical factors there that can be canceled out. So this is the fully simplified version of this original expression, and that makes that your final answer. Okay, guys, so those are 3 examples that illustrate the concept of how to simplify rational expressions. Now we're going to move on into multiplying rational expressions, but the really good news for you guys is this is not really much harder at all than the problems we just did. But let's knock out our key concept right here. Taking you back to 5th grade, how do you multiply 2 fractions? A over B times C over D? Well, the really good news here with multiplying and dividing, you don't need a common denominator. All you do is you multiply your numerators. A times C is going to get us AC. That's your new numerator. And you multiply your denominators. B times D is just BD. And that's it. That's how you multiply 2 fractions. So when you were in 5th grade, they probably gave you some problems like, let me see if I can do this right, like 2/5 multiplied by 4/7. So what did you do here, guys? You multiplied the 2 times the 4 to get an 8, 5 times a 7 to get a 35. Simplify if you can, which you can't. There's your answer. So multiplying fractions is much, much easier than adding fractions because you don't have to worry about a common denominator. Now, sometimes it gets a little bit tougher with canceling out, but I tell you what, let's just dive into this first example and we'll kind of see that in action right here. So we've got these messy algebraic fractions. These are what we would call rational expressions, 2 of them being multiplied together. So what I could do, everybody, is multiply my numerators together. Now, don't do this because I'm going to show you why this gets messy in a hurry, but we could multiply 12 times 35, which if I'm not mistaken, let me think, 35 times, 4 is 140 times 3. I think that's a 420 up on the top. And on the bottom, 25 times 24 is going to be 600, but now I've got to come and simplify all that in just a hurry. So I'm going to go ahead and show you guys the way we're going to handle this in Algebra 2, not just the way we would do it as an elementary or a middle school kid. What I'm going to do is look at the 4 numerical coefficients in this problem. A 12 on the top, a 25 on the bottom, a 35 on the top, and a 24 on the bottom. And I'm going to look for identical factors that can be canceled out. Like, for example, the first one I notice is that 25 and 35 are both divisible by 5. So let me go ahead and divide a 5 out. 35 divided by 5 leaves me with a 7. 25 divided by 5 leaves me with a 5. And now I have much smaller numbers to work with. How about this 12 right here and this 24? They're both divisible by, and remember, think as big as you can. They're both divisible by 12. 12 divided by 12 is 1. 24 divided by 12 is 2. So now look how easy this just became. My numerator's coefficient is the product of 1 times 7 which is 7. And my denominator's coefficient is 5 times 2, which is 10. That was a lot easier than what did I have? 420 divided by 600 and then trying to find what goes in there. Okay, what else can we do here, guys? Now with the variables, I think I might do this one pretty straightforward. Take a look at your numerator. X to the 4th times x to the 6th. This is when we add x's together. That becomes, exponents together. This is how we get x to the 10th, because this is x times x times x times x. And this one over here is, oh boy, x times x times x times x times x times x. How many x's is that? 4 of them here, 6 of them here. That's how we end up with 10 of them. How many y's are in the numerator? I've got y to the 5th, and that's it. So it's just y to the 5th upstairs. Now in the denominator, we have x multiplied by x to the 4th. And remember, guys, that's x to the 1st power. So add your exponents together, 1 plus 4, we end up with x to the 5th power. And down in the denominator, y to the 6th times y to the 3rd is going to be y to the 9th. Now, one thing I'd like you guys to learn, hopefully sooner rather than later, this, what I have written right now, cannot possibly be your final answer, because you're never allowed to have the same variable on both the top and the bottom of a rational expression. It's got to be simplified. So there's nothing else you can do with the 7 and the 10. But let's talk about x's. Which side has the bigger army here? That would be the numerator. 10 is bigger than 5, and we just subtract. 10 minus 5 means we're going to end up with 5 x's in the numerator. Now, how about the y's? 5 on the top, 9 on the bottom. So the bottom is going to win the war of the y's. And how many are going to be left standing? 5 will cancel. 9 minus 5 is going to leave us with 4. And that's our answer here for example 2a. Okay, so with monomials, like we had right here, you can kind of forget about step number 1 we talked about a while ago, which is factoring, and you can really just dive right into this canceling thing, okay? So there's not really much factoring to do with monomials, but when we move on to an example like this, where you have polynomials, we are going to have to factor here before we cancel. And what do we see here, guys? We've got 1, 2, 3, 4 polynomials. All of them, each one, is going to have to get factored before we can start doing any canceling. Okay, so what do we got here, guys? X squared plus 9x plus 20. No GCF, but it looks like a quadratic trinomial. What times what is x squared? That'll be x times x. The signs are going to be the same and both positive. So plus, plus, and we need two numbers now that multiply to 20 and add up to 9. Sounds like a 4 and a 5 to me. Underneath that, x squared minus 9 is another difference of squares. So that's going to factor into x and x. Signs with a difference of squares are always 1 plus, 1 minus. And then the square root of 9 is going to be a 3 here and a 3 here. Okay, half done with the factoring. Top right, x squared plus 6x plus 9. Again, no GCF, so I'm going to try reverse FOIL. The x squared splits up into x times x. Signs, again, are going to be the same and both positive. So plus, plus. And we need two numbers that multiply to 9 and add up to 6. Sounds like it's going to be 3 and 3. Bottom right, it looks like we have another difference of squares. The x squared splits up into x and x. With a difference of squares, your signs are always 1 plus and 1 minus, and then the square root of 25 is going to be a 5 that goes here and here. So that is all of the factoring, you guys. And now, what can we cancel? Identical factors on both the numerator and the denominator cancel out. So what do we see? An x plus 5 on the top here and an x plus 5 on the bottom here. Okay, got it. What else? I see an x plus 3 on top and an x plus 3 on bottom. Got it. And that looks like it. I don't think there's anything else right here that are identical factors on the top and bottom. So everything left over is part of your answer. X plus 4 multiplied by, at the end, an x plus 3 all over. We have an x minus 3 in the denominator times an x minus 5. And that is as much as you can do to simplify that expression right there. So factor first, cancel out, and then just write what's left over. All right. And that's basically the multiplication of rational expressions in a nutshell. And let's move on to the last piece we're going to do here, dividing rational expressions. And I just need to refresh your memory from 5th grade here one more time. The key concept here, if you're going to divide two fractions, w over x divided by y over z, you leave the first fraction the same as it was, w over x. And here's what I'm hoping you guys remember. Dividing by a fraction is the same as multiplying by the reciprocal of that fraction. So we flip the second fraction, y over z, and make it become z over y. Then, this is just like what we were doing on the last problem. You multiply your numerators to get wz and your denominators to get xy, and that's your answer there. So dividing takes an extra step. You've got to turn division into multiplication, and then you can go ahead and do what we were just doing in the last two problems. So 2 examples, and then we're done here, guys. Again, let's look at this with monomials first. We've got a rational expression divided by a second rational expression. So what are we going to do? We recopy the first one, 9a to the 5th, over 20b to the 7th. We change the division to multiplication, and then we reciprocate the second fraction. The 45b to the 7th now comes up to the top, and the 18a cubed now goes to the bottom. Now, we could multiply 9 times 45, big number, and 20 times 18, another big number, or we could start looking for common factors that can be divided out. That's the way to go. So I see a 9 here and an 18 here. They can both be divided by 9. 9 divided by 9 is 1. 18 divided by 9 is 2. How about this 20 and this 45? Those are both divisible by 5. 20 divided by 5 is 4. 45 divided by 5 is 9. So what does that do for our answer here, guys? In the numerator, 1 times 9 is 9. And in the denominator, 4 times 2 is going to be 8. In the numerator, let's do variables here. I've got a to the 5th and then b to the 7th. Nothing really combines there. And in the bottom, yeah, okay, I've got an a to the 3rd, just trying to do that in alphabetical order, and a b to the 7th as well. So what can we do to clean that up? Nothing can be done with 9 over 8. That just stays. With the a's, there's 5 of them on top, 3 of them on bottom. So the a's are going to end up on top, and how many are left after their war? 5 minus 3 leaves me with 2 a's that are left. And then where do the b's end up? Nowhere. We have equal-sized armies. The b to the 7th cancel each other out completely, and so all we end up with then is 9a squared over 8. The b's are completely gone because we have the same number on both the top and the bottom. So that would be a division problem with 2 rational expressions that have monomials on both sides. And the last example I have for you here, guys, is just a little bit more complicated than that. It's the division of 2 rational expressions, but both of which contain polynomials and not monomials. So again, the 2 steps right here, guys, we need to factor and we need to cancel. But I guess before that, I should take an extra moment and rewrite this division problem as multiplication. The first fraction stays the same, x squared plus x minus 42, all over x squared minus 13x plus 12. Now we'll change the division into multiplication, and we'll reciprocate the second fraction. 144 minus x squared all over x squared plus 19x and a plus 84. So let's knock the easy stuff out here first, guys. We change division now into multiplication. Now let's start factoring, and this is where this one's going to get a little bit more challenging, so here we go. Quadratic trinomials all over the place, guys. The x squared in the top left breaks up into x times x. Now I look here, and because c is negative, that tells me these 2 signs are different. 1 plus and 1 minus. So I need 2 numbers that multiply to negative 42 and add up to a positive 1. That is going to be a positive 7 and a negative 6. Got it. Down in the bottom now, x squared minus 13x plus 12. Let's try to do the same thing again. The x squared splits up into x times x. Now, this plus here tells me that these two signs are going to be the same, so now I look here and I see, they're both negative. Two numbers that multiply to 12 and add up to a negative 13 is going to be a negative 1 and a negative 12. Okay, that's all the factoring from the first one. Top right is something that bothers people sometimes. 144 minus x squared. There's no GCF to pull out, so what I want you to notice is it's a binomial, and there's only three kinds of binomials that we've learned how to factor so far this year, guys. A difference of squares, a difference of cubes, and a sum of cubes. This one is a difference of squares, because 144 and x squared are both perfect squares. So again, it factors into the product of two conjugate binomials. What's the square root of 144? 12. So that goes here and here. Signs are always going to be 1 plus and 1 minus, and then the square root of x squared is x. That goes here and here. Now, that's a little out of order. I know you guys don't like it when the 12 comes first and then the x, but too bad. You got to deal with it that way. You don't get to switch it around just because you don't like it. Now, in the bottom right, let's see what we've got here. One last bit of factoring here, guys. The x squared splits up into x times x. The signs here are going to be the same, and this time both positive. So plus, and we need two numbers now that multiply to 84 and add up to 19. 84 is kind of one of those numbers we should have learned back in the day, and I'm not sure we did. That's 12 times 7, and as luck would have it, that adds up to 19. So I'm going to put a 12 here and a 7 here. All right, guys, what happens then? Now that we've done all of our factoring, we're now looking for identical factors, top and bottom, that can be canceled out. So what do we see? An x plus 7 on the top cancels with an x plus 7 on the bottom. This one's a little tricky. 12 plus x in the numerator and x plus 12 in the denominator. Guys, the order of addition doesn't matter. So 12 plus x and x plus 12 are exactly the same thing. They cancel each other out. But now that I've said that, let's look at what's going on here and here. I just got done telling you right here that the order of addition doesn't matter, so those two factors, can be canceled. But does the order of subtraction matter? Well, the answer to that is yes, sort of. 12 minus x and x minus 12 are not the same thing, but they are related. Let me show you guys what I mean real quick. If I gave you a fraction and asked you to just pick two numbers, like, I don't know, 10 minus 7, and then in the denominator, change the order, make it 7 minus 10, let's see what happens here. Your numerator, 10 minus 7, is 3, and your denominator, 7 minus 10, is negative 3. And 3 divided by negative 3 is negative 1. Let's try that experiment with something different. What if I gave you 13 minus 4 on the top and then 4 minus 13 on the bottom? Well, 13 minus 4 is 9, but on the bottom, 4 minus 13 is negative 9, and 9 divided by negative 9 is negative 1. So what you guys have maybe never put together here is that when you change the order of subtraction, 10 minus 7 compared to 7 minus 10, you end up with opposite results. A positive number on one side and its opposite on the other. And anytime you divide a number by its opposite, you always get a quotient of negative 1. So back to this problem at hand, do the x minus 12 and the 12 minus x cancel? Sort of. They divide out, okay, so you can cross them, but they always leave a product of negative 1 in their wake anytime you're canceling out two factors that are reverse subtraction expressions. In this case, x minus 12 and 12 minus x. And that's really it, you guys, for what we can cancel out. So what are we left with? My numerator has a negative 1 out in front and then an x minus 6 at the end of that, and that's it for the numerator. all over my denominator, which is x minus 1. Now, I would be perfectly fine if you guys left this as your final answer, but I just want to warn you, one thing it wouldn't shock me to see is if somebody who wrote the answers to a worksheet or a book problem distributed that negative 1 in there and got negative x plus 6 over x minus 1. And if they did that, there's a very good chance they might change the order on the top and make that positive 6 minus x all over x minus 1. So honestly, you guys, any of those three versions of the answer would be correct and would get you full credit. All three of those are equivalent. All three of those are fine. All right, everybody, so that is a wrap on our notes on section 8.4. So let's give that homework a try. Just remember the two big things you have to worry about, guys. Factor first, and then try to cancel with what's left over. Okay, good luck on the 8.4 homework, everybody.